Welcome to Chapter 1, Section 1, Methods of Science. And in this section, the main idea is that scientific investigations do not always proceed with identical steps, but do contain similar methods. Take a moment to fill out what you know about the methods of science and what you would like to find out. In this section, we are going to answer 4 essential questions. First is, what are the characteristics of scientific methods? Why do scientists use models? What is the difference between a scientific theory and a scientific law? And what are some limitations of science? Here's a list of some vocabulary that we're going to discuss in this section. Some you may have seen, some you may have not. So, what is physics? Well, physics is a branch of science that involves the study of the physical world. So, when we talk about the physical world, we're talking about energy and matter and how all of those interact with each other. I'm sure that you've seen this definition from the National Academy of Science being the use of evidence to form testable explanations and make predictions about natural phenomena, as well as the knowledge generated through this process. And so that's just the basic idea of what science is, and we are going to operate and study physics under that definition. In doing that, physicists will use something called scientific methods, and these methods are going to be very similar to the methods that were used in biology or chemistry or in your environmental science classes, but they may be different depending on the situation. And although they don't follow a rigid set of steps, physicists do use particular methods to study natural phenomena. In physics, many investigations begin with a question of why or how. And so we might see an event happen and we ask ourselves, why did that happen? Or how did that happen? We see a plane flying through the sky and we might ask, how does that stay in the air when it's really heavy? Or we hear the noise of the plane after it's passing us, and we might ask, why do we have a delay in the sound in compared to the event that we see? And so if you research information that's already known about a particular situation, you can then find a more fine-tuned question to ask about the situation. And this is where you will form a hypothesis. And that's a possible explanation for a problem using what we know and have observed. Then we want to look to test the hypothesis, and hypotheses can be tested by observations, by models, or by experiments. The key with using experiments is you typically use a control, or you test the effect of one thing on another. An important part of any investigation is collecting and organizing the data that you use. Typically, we're going to use easy-to-read tables or graphs, and then based on the analysis, the next step, you decide whether the hypothesis is supported or if it is denied. If you claim that it is supported, then the data must be reproducible many times. So that's typically why we will do experiments over and over and over again, to make sure that it wasn't just a coincidence or a fluke, but the data is reproducible. And if it's not supported, the hypothesis must be reconsidered. In physics, we will often use models to display or to explain something. And a model is simply a relationship of an idea or an event, structure, or an object that helps people better understand it. And we'll use models with an object that is too large or too small, or a process that takes too much time to see completely, or possibly a material that's hazardous. So talking hazardous material, something like the material that's radioactive, we might use a model to talk about that instead of actually using the material, because that could cause harm to others. Some examples of models are listed below here. And so we have the quantum model of an atom. Well, we can't actually see that. That's really, really small and hard to see. So we create a model to represent what's going on. Same thing for the gravitational field of the Earth. Once again, very, very big scale, and so it's hard for us to see that point of view, so we create a model. And then looking at the ray model of light, this just shows how photons may go out in a linear path or a gradient path, and the model helps represent what the photons are doing when we see light. So scientists, after making observations, they'll come up with explanations and they'll explain what they see. And we call these scientific theories. And scientific theories are explanations of things or events based upon knowledge gained from many observations and investigations. The key is this is not a hypothesis. This is what a hypothesis becomes after numerous trials and supporting data. So if you have a hypothesis that you think is a possible explanation, and then you can support it with reproducible data, then it can become a scientific theory. A theory is never permanent, and that's one thing that's important. It can change as new data and information becomes available. So scientific theories are constantly changing. We even have theories today that change or are tweaked into a new form when new data comes out. Whereas a scientific law is a statement about what happens in nature and seems to be true all the time. We can't find anything or we can't observe anything that shows that maybe the law is not true. And so laws tell you what will happen under certain conditions, but they do not explain why or how something happens. And that's important. There isn't the why or how, it's just we know that something's going to happen. And a great example of this is gravity. We know the law of gravity states that any one mass will attract another mass. And so there are many theories proposed to explain how the law of gravity works, but the law of gravity just states that masses will attract each other. Or in other words, if you drop something, it's going to fall toward the earth. Why that happens or how that happens, there isn't a law explaining that. There are many theories that give explanation, but some of those still aren't proven. There are limitations to science, and science cannot explain or solve every question. And the scientific question must be testable and verifiable. And some questions just aren't. And so questions about opinions, values, or emotions are not scientific because they cannot be tested. And so if you look at a list of these questions down below here, it can give you an idea of what science can do and what it cannot do. So if we want to look at how does a force change the motion of an object, science can answer that question because we can devise tests and we can make observations. But if we want to answer the question, which season is best, well, that's an opinion. So science really can't do anything about that. And how does a battery work? Well, science can answer that question. Was Mark Twain a good writer? Well, once again, that's opinion. That's not searching for a fact or a piece of knowledge. And should we have pizza or hamburgers for lunch? Well, once again, that's an opinion. Science can't help you with that. However, science can answer under what conditions is energy conserved and can a plant live without light. Those are both testable and verifiable. So to finish up this section, make sure you can answer the 4 essential questions. What are the characteristics of scientific methods? Why do scientists use models? What is the difference between a scientific theory and scientific law? And what are some limitations of science? Also, here are the key vocabulary terms that you will need to know from this section. Moving on into Section 2, Mathematics and Physics, the main idea of this section is that we use math to express concepts in physics. Mathematics is said to be the language of physics or the language of the universe. So before moving on to the video, I want you to write down what do you know and what do you want to find out about the relationship between mathematics and physics. And then after the video, you can write down what you have learned. The 3 essential questions we are going to answer in this video are: why do scientists use the metric system? How can dimensional analysis help evaluate answers? And what are significant figures? Only a couple new vocabulary terms of dimensional analysis and significant figures. And in case you don't remember what SI stands for, that is actually a French term. We don't need to know the French, but we just know SI means our standard international units that we're going to use. So why is there so much math in physics? Well, physicists often use math as their language, and physicists rely on theories and experiments, and those experiments typically have numerical results to support their conclusions. So it takes something that may be conceptual or something that is qualitative, if you will, and it turns it into something quantifiable or quantitative, meaning we can have a specific number that represents a situation. And with numbers comes mathematics. So the units that we're going to use in physics are an adaptation of the metric system that are called the SI units. And that's, like I said before, a French term here talking about the International System of Units. And this is the metric system. Most countries, actually all but the United States, use this as their standard unit of measure for everything. We still use the British units of pounds and feet and inches and all that. Whereas in this class, we're going to use the SI base units. And so this table is very helpful to tell you, well, when we're talking length, what are we going to use? We're going to use a meter, and the symbol is M. When we want to look at temperature, we're going to use Kelvin, and this symbol is K. So we won't use Fahrenheit, and we won't use Celsius for temperature. We'll use Kelvin. Now, these are not the only units in the SI system. There are other units called derived units, which are basically just combinations of these base units. And so as we introduce a new derived unit, we may give it a new name just because it may become a mouthful to say kilogram meter per second squared. Well, instead of that, we'll give it a new name, and you'll see that when that comes. In using the SI system or the metric system, since it is a base 10, we do have prefixes to denote the power of 10. All of these prefixes should be committed to memory at some point. Now, you may know some of these. Right off the bat, you may know what is milli and centi and deci and possibly even up to kilo and mega. And, with computers, we use gigahertz a lot of times. There's 1 gigabyte of memory, or even computers up to terabytes of memory. So you may have a concept of what these are. Where you may have a deficiency is in the smaller prefixes. So make sure you know these all the way from femto up to tera. Until you have those memorized, this table will be a great resource for you. In many of our problems in physics, we're going to need to be confident in our practice of dimensional analysis. And dimensional analysis is a method of treating the units as algebraic quantities, which can be canceled. We're going to go over a couple examples of this. And we can use this to check that you have set up a problem correctly, or check that your answer has the correct units, and to choose a conversion factor. So say we want to convert 43 kilometers per hour into meters per second. Now, both of these are units of velocity or speed, depending on the situation. You'll find out the difference between velocity and speed next chapter. But we want to convert from 43 kilometers per hour to meters per second. We want to know how many meters per second is that. And so we can use the process of dimensional analysis. And we multiply by all these different factors that are all equivalent to 1. And if you notice, 1,000 meters is 1 kilometer. 1 hour is 60 minutes. 1 minute is 60 seconds. Now, where did we get those? Well, we knew that we wanted to take this kilometer and get rid of it because we start with kilometers and we need to end up in meters. So to cancel out the kilometers, since it's in the numerator, we need to have a kilometer in the bottom. Well, what is 1 kilometer? Well, 1 kilometer, it could be a host of different things, but we know we want to end up with meters, so we know there are 1,000 meters in 1 kilometer. So that's our first conversion factor. And when we multiply by that factor, the kilometers cancel, and we're just left with a number of meters per hour. Well, we don't want to end up in hours, we want to end up in seconds, so we need to get rid of the hours. Well, we know 1 hour is equal to 60 minutes, so we multiply by 1 hour over 60 minutes, so that way the hour in the bottom cancels with the hour in the top. And then we need to get rid of those minutes, so we put 1 minute on top over here, and how many seconds is that? Well, that's 60 seconds, and so those minutes cancel, and we're left with seconds on the bottom, meters on the top, and we just do the computation here, 43 times 1,000 times 1 times 1, divided by the product of 1 times 1 times 60, or 43,000 divided by 3,600, and we get 12 meters per second. So let's practice a problem here. Let's convert 32 centimeters per second to kilometers per hour. So let's start by writing the 32 centimeters per second. And we have centimeters on top, but we want to get to kilometers. And we have seconds on the bottom, and we want to get to hours. So we just have to pick one of those that we want to get rid of first. So let's get rid of the seconds first. So we know that 60 seconds is equal to 1 minute. And so that will cancel the seconds there. So there's our first conversion factor. And then if we multiply by 60 minutes, are in 1 hour. Now, why did I have minutes over hour? Well, I know that I wanted to get rid of these minutes in the bottom, so I need to have minutes up top. So that gets me hours in the bottom, which is what I want. I need to have hours in the bottom. And so now we need to work on the centimeters. We need to get rid of the centimeters. Well, I know that 1 meter is 100 centimeters. And so that centimeters will cancel with that centimeters. And that gives me meters, but I want kilometers. So I know that 1 kilometer is equal to 1,000 meters. And so that meter cancels with that meter, and I'm left with kilometers in the numerator, hours in the denominator, and that's what I want. And so all I have to do is just multiply the top across, 32 times 60 times 60, multiply the bottom across, 100 times 1,000, divide those, and then we get 1.2 kilometers per hour. And I know I went through that quickly, but we'll practice some more of these in class. We can also use this to determine the units of energy using the formula from kinetic energy. And we know the formula from kinetic energy is really it's 1/2 the mass times the velocity squared, but more importantly, it's just the mass times the velocity squared. And so if we look at mass is kilograms, velocity is meters per second, when we square that, we get kilograms meters squared per second squared. And so that tells us the units for energy in the base units. And like I said before, we will give that a new name when we start talking about energy. All measurements are approximate and have significant figures, and it's the last digit given for any measurement is the uncertain digit because of rounding. Significant figures are the valid digit in a measurement. So let's say we have a ruler here, and we're trying to measure this piece of whatever it may be. And so looking at the two different rulers, we have a centimeter ruler and we have a millimeter ruler. Using the top ruler, we see that the measurement somewhere in here, which is between 9.5 centimeters and 9.6 centimeters. And using the lower, we just know that it's somewhere in between 9 and 10. The upper ruler we estimate to the nearest hundredth of a centimeter, whereas the lower ruler we estimate to the nearest tenth of a centimeter. And so looking at this, you can begin to see that two different types of measuring tools can give us two different significant measurements. A few significant figure rules to live by are first that non-zero digits are significant, final zeros after a decimal point are significant, zeros between two significant figures are significant, zeros used only as a placeholder are not significant. So the difference is the 100, these are just placeholders, those zeros are not significant. 101, that is significant. So this has 3 significant digits, this only has 1. If we have exact numbers like counting numbers 1, 2, 3, 4, 5, those have an infinite number of significant figures, and conversion factors have an infinite number of significant figures. So we're saying that they're exact. Their significance goes on forever. You can take a moment and look at these practice problems here by stating the significant figures in each measurement, and you see the answers are listed in red. So this 5.0 milliliters has 2 significant figures because that 0 after the decimal place is significant. That is not just a placeholder, like in this 4th example where 10,500, those 2 zeros are placeholders, so we only have 3 significant figures. Now, where this comes into play is when we add or subtract or multiply or divide these numbers together, we have to have our final answer in the number of significant figures of the lowest or the average of the number of significant figures. So look at this first example here. We have 4 significant figures, 2 and 3. So we have an option. We could either just list the answer as 2 significant digits, or we could say, well, let's use the average. Since this one has 4, that is 3, that is 2, the average would be 3. So when we add those together, we list it as 10.7. But we wouldn't list any more than that. Looking at the next one, 3.4 divided by 6.5, we have 2 significant digits, 3 significant digits, so we default to the lowest, 0.52 meters per second. We don't continue on past the 2. Same thing with these last 2 examples. So reviewing this section, hopefully you are able to answer the 3 essential questions of why do scientists use the metric system, how can dimensional analysis help evaluate answers, and what are significant figures.